Okay, I think we are. Rio, what do you think? Should we start or wait a little bit longer?
Um, I think we should start because of time. Yeah, it's people are still joining, but
Okay, well, that's pretty good. We still have a very brief introduction to let people join and get comfy. So, good afternoon and welcome all to the Industrial Ecology Day and to our special session. I'm very pleased to see that many people were able to join. We are very happy for that and thank you. My name is Gustavo Larrea, and I'm a researcher at the Luxembourg Institute of Science and Technology. And today I'll be your moderator and I'll be guiding you throughout the whole session. This session is organized by the Lifecycle Thinking for Complex Systems initiative, and it brings today very nice three presentations that will show us how can we use complexity-oriented methods such as agent-based modeling to address different research questions that are common in the industrial ecology field. Now, before going to the presentations, I would like to ask you to please join the following Mentimeter session. You can see the QR on the slides by scanning this code or by going to menti.com and typing the number that you see. From now on, you will be able to submit questions during the series of presentations because we have a very big number of registrations. We're going to be managing the questions using Mentimeter. We'll also use this Menti session during the interactive part. So please, once you join, stay connected. Now, before starting, I would like to give a very brief introduction to explain a little bit what is the relevance of this topic and also what is the context in which we organize this session. So to begin, one of the main questions that we hopefully will answer by the end of this session is, why do we need complexity science methods in industrial ecology? Well, in industrial ecology, we study the systemic relationships between society, economy, and natural environment. These dimensions are interconnecting among each other because of production and consumption systems. Now, the main issue with production and consumption systems is that they are complex because they are highly intertwined networks that result from the interaction of these very tiny individuals that we call humans. And this fact has motivating to treat and study production and consumption systems as complex systems. Formally speaking, a complex system can be defined as an ensemble of elements that are interacting among each other. And the identity of the whole system is determined by its elements, and at the same time, the identity of the elements is determined by the whole system. Now, simultaneously, these systems are also adaptive because they respond and adapt to exogenous and endogenous changes. Finally, something very important to mention is that we are not dealing with simply technological systems, but socio-technical systems, because production and consumption systems are networks of social agents that are constrained by some technical characteristics. Now, being this said, in this context, agent-based modeling has arisen as a popular paradigm for studying these complex systems, such as socio-technical systems. In a nutshell, agent-based modeling, or ABM, it's a bottom-up modeling paradigm in which the system behavior emerges from the interaction of the agents. In ABM, we represent the system in a computational manner, and we acknowledge reality as a composition of autonomous and independent agents. These agents are the reducible elements of the model, and they can represent humans, companies, or even ecological entities. So it's in this context in which the initiative that organized this session has been created. The Lifecycle Thinking for Complex Systems initiative is basically, we're a group of young researchers that share a common interest on understanding the sustainability of complex systems. For this purpose, as you will see today, we commonly combine tools that are well known in the industrial ecology field, such as life cycle assessment, with methods like agent-based modeling to model and to study complex systems such as socio-technical or techno-ecological systems. One of the main purposes of the initiative is to promote the use of complexity-oriented methods in combination with life cycle thinking approaches. For this, of course, we want to provide a platform or a space for exchanging ideas and to promote the engagement beyond different academic domains. Yes. So, being this said, this session is, of course, one step in this long path that we are willing to walk. And without further delay, I would like to introduce our first presenter, not without reminding you to please join the Mentimeter session, scan the QR. You can from now start posting your questions or put the code number in the website. So Jonathan Cohen is a researcher at the Chalmers University of Technology. He's our first presenter, and welcome, Jonathan. The floor is yours.
Yes, I just sent a request.
I think, Rio, could you help me with us?
Yes. So thanks. Can you see the presentation, Gustavo?
Yes, I can see it.
Yes. Okay. Thanks and welcome all to this short showcasing application that I've been working at Chalmers. I'm a postdoc researcher working together with Maud Lano, George Gill, and Leonardo Rosado. We've been working in the construction and demolition sector. For the ones that are joining, please, if you have any questions, join the same Mentimeter so we can compile all the questions and queries that you have for all of us. So without further ado, as we know, we are living beyond our planetary boundaries. Since 1970s, the material consumption and extraction of raw materials has been almost doubled, and that has been associated with negative implications in our environment that goes beyond only carbon emissions or rising in temperatures and waters. The construction sector in this challenge plays a significant role because not only they are responsible for a lot of material extraction, roughly half of it's needed to develop a sustainable built environment, but also in terms of water usage and almost waste generation. To this end, we know that a lot of policies have been in place, the European Union Green Deal, but specifically there are specific targets that goes to how much waste has to be reduced and how much materials needs to be put for reuse within the European Union. Following the same, our study is trying to demonstrate the potential of material stock-driven simulations to evaluate environmental impacts related to the construction and demolition activities. For this, I will be showcasing today the rule-based simulation about these activities, but also to try to understand how these models can become useful for policy scenarios and for evaluation. The framework that I have been using to develop the agent-based model follows Stedman's system dynamics, and it has been adjusted, but pretty much from the problem that I have stated. We go into the modeling, the rules and heuristics of the model, and then looking at the case study and the data, we start to redefine the model and what is possible. And once we achieve a place of stability about the model itself, then we go in and run simulations and sensibility analysis to understand to what extent different parameters affect the outcomes that we are looking. In our model, I developed 4 agents, which is the building itself, and is the main agent of my model. And then we have a recycler, which is compiling all the waste that is being generating and works as a mediator for new constructions, a planner that is a gateway to understand what can be built in different parts of the city. And finally, we have to have an object that retains all the information. And in this case, is the city area with subdivisions to understand where there could be future constructions. Conceptually, the model has a supply of material component, which is built based on the demolitions of the buildings and renovations that also generate the material supply. And on the other hand, there is a material demand of these materials that are triggered by the population increase, which it's requiring more buildings. And then also demolitions needs to be accounted because there's building stock that needs to be replenished. And finally, renovations of buildings are also requiring new materials. So our main agent, again, is each one building. So every building in our model follows the same process and the same rules, which is based on this simple diagram, which pretty much tell us that each building, when it comes to its potential year of demolition, which is established based on statistics of the location, it undergoes a decision process whether it's going to be renovated or demolished. If it goes under the renovation, their life of the building is expanded. And then if it goes under demolition, the building gets out of the model, but the materials are being collected through the recycler. So once we establish this rule base, which is a bit more complex in the model and the code, we then had to go into data gathering for all this model, which implies building material stock database, material intensity coefficient, the demographics, and also starting to work with embodied carbon of all of these materials. Once we have our case study, our system delimitation, then we run the model and we started to explore the simulations. So for our purpose and to demonstrate what can be achieved with this model, we use our city, which is Gothenburg, and we have been developing a lot of data and data processes to refine more and more the database. So in this case, this is Gothenburg. And then within the buildings of Gothenburg, we managed to extract the materials that were embodied in each of these buildings. And this is an example of a single family unit and a multifamily unit. And this is what we're going to use for future constructions for in terms of material needs. And then within these 8 materials, such as wood, wool, brick, concrete, glass, etc., we made an association regarding the embodied carbon that these materials have based on national statistics. And for each of these materials were selected, we started to calculate and we managed to have a material stock and the embodied carbon of the built environment for residential buildings. All of this was crafted together into Gamma, and this is how our platform looks. So to the left, you can see the panels that we are going to be working with, but also the different displays and the different key performance indicators that we're interested in following. So as we can see in the control panel, we can work with the rate of renovation that these buildings will have, the probability for them to be renovated, how much percentage of materials could be used for new buildings, but also for renovations. And then we're also exploring the morphological aspect of these buildings, which is the percentage of single family to resident to multifamily buildings. Finally, a policy scenario was explored in relation to whether energy performances of buildings will have some sort of restrictions in the future, which will imply possible forced renovations or demolitions, but also the new buildings that has to be built needs to have a certain standard. So here you can see the model running itself. Each of these buildings in the map is it's one agent, so it's roughly running around 60,000 buildings all at the same time, and they're exploring these opportunities with a specification of how much materials is going to be circulated. And then after we run all the simulations, we rerun these several times under different parameters. And for instance, we could start to explore how does the material demand of the city changes as the percentage of demolition changes and the percentage of single family and multifamily changes. So in Gothenburg, for instance, there's a lot of brick buildings that were developed in around the 70s, 80s. So if these are demolished, there's going to be availability of this material. So this is, in terms of policy, can provide quite useful insights for future development of the city. Also, we can start to measure the embodied carbon of the city overall and how much could be captured by these circular economy strategies. So we were exploring also the temporal aspect in the perspective in a prospective way. And this can also lead to understand how these different variables can impact the embodied carbon of the city. So we are able to understand to what extent different probabilities of demolishing or different probabilities of renovation, how much do they impact the overall embodied carbon. But what is novel about our technique and our method is that we can start to map the results into specific locations because we have all the buildings of Gothenburg. So this gives us a possibility of understanding where demolitions are going to happen and where the material availability will become available and what type. Finally, this was even extended into policy scenarios, so we could start to see what would happen in a scenario where specific energy performance of buildings are restricted. So in the left case, we run the model without restrictions, and into the right, we run the model with an energy performance restriction for the lowest class. So you can see that the red line at the end of the graph is flattened because we are not longer accepting specific type of buildings in this scenario. So our contributions have been to estimate future scenarios of various circular economy strategies. With this method, we can determine spatio-temporal location of materials needs and availability, but also we can develop a model with general rules that can be adopted to other case studies as long as specific data is provided. In relation to limitations and future work, we would like to understand how we can extend the methodology to go beyond 8 materials and to go to the life cycle of specific building components. And this is going to be very computationally expensive. But also we can start to think of if there are other ways of modeling these agent-based model and simulations and going into a more network or graph-based simulation where the building itself could be broken into different nodes, such as site, structure, skin, service, and so on. And finally, but not least, just to note, although we work only with embodied carbon equivalents, it's also not to lose track of the global aim that we have to go beyond circular carbon emissions, but also to look at other climate change problems, such as acidification or loss of biodiversity. This work has been developed together with Maud Lenaud, George Gill, and Leonardo Rosado, and I will be here until the end of the seminar in case you have any questions. Thanks so much for listening. Gustavo, now it's you.
Thank you very much, Jonathan. And very interesting presentation. As a reminder, we're going to be addressing questions at the end of the 3 presentations. You can start, sorry for that. Yes, you can submit your questions joining the Mentimeter code that was previously presented. And now I would like to invite Tianren Ding. She is a researcher at Luxembourg Institute of Science and Technology. And please, Tianren, the floor is yours.
It's not yet a presentation mode, Tianren. Yes, good.
So hello, I'm Tianren Ding, and from the Luxembourg Institute of Technology. So this work I'm going to present is from the work in where I did my PhD in University of Brussels, and which was funded by the FNRS. So the aim of this work was to combine agent-based modeling with territorial LCA to support agricultural land use planning. So I'm going to, so for the bioenergy, we have all heard of it, that it's good, it's renewable, and it could help the rural economy to grow. So many of us think we need to adopt it. But in the situation for the adoption decision is from the farmers, even though the policymaker will say that we think it's good, so we want to have it, but the farmers will think about some other factors, like I don't know the technology, I'm not sure if it is real profitable. So the farmers might say no. But then if the policymaker provides enough incentives, then the farmers might say, okay, I don't know the technology, but I will try this year. And more within the over years, and then farmers might have more, we will have more farmers adopting these bioenergy crops, and we might reach our regional targets. For example, have the bioenergy production to support the energy system of the region 20% or 10%. But that is the ideal world. But in the complex real world, we need to know if our bioenergy is really green enough. So we need to have assessment method to do that. And we also need to know how farmers will make that decisions. So we need to have the method to simulate farmers' decisions. For assessment, we need the assessment tool to have at least these 4 criteria to make sure that it's comprehensive. It should be at the territorial level. We don't want to see, we don't want to know only one product. We want to see the impact at the territory. We want to know if it is spatial specific, because each location have their own soil properties, for example. So the spatial dimension is important. And then we want to see the production life cycle instead of focusing on one product, one process. And then we want to have the multi-criteria. We don't want to only focus on the climate change. We want to see what will be the impacts on the eutrophication and other indicators that we care about. So in that sense, territorial life cycle assessment was developed in 2013 at that moment. And this method was developed based on LCA, but focusing on the territorial level. It starts by giving you a scenario of land use. So in this case, we have land use 1 and land use 2 in this specific allocation. And this scenario, after run the territorial life cycle assessment method, we will know what is the environmental impacts, including different indicators, for example, climate change or freshwater eutrophication. And another vector we will know is the land use function that we care about. If what will be the economic production, economic growth, or bioenergy production or food production. So this method was developed for this purpose. But this method doesn't think about the spatial dimension. So if the land use 1 is located on the bottom of this scenario, of this territory, will have exactly the same profile if they are located on the upper side. Therefore, we want to have the spatialized territorial life cycle assessment. We want to link with the GIS model so that we could know at which location what land use scenario with the specific spatial allocation. And in that sense, we could know when we introduce new land use where maybe it could have a higher impact, where they will have low impact. On the other hand, for the farmers side, the farmers are influenced by multiple factors. They are willingness to adopt energy crop is low, or their ability to adopt is not that high. So at the initial time series, we have an initial land use scenario, and once the farmers start to adopt the energy crop with the incentives, and it will have higher influences and have more adoption rate over the time series. So this is the what can be achieved using agent-based model. Our aim is to link these two together using spatial territorial LCA with agent-based modeling so that we could all achieve these features in our model. So we start by using the simulation to see the future land use, and then we evaluate with the spatial territorial LCA. And then this structure is from the LCA structure, but specifically for the inventory, we will obtain our land use scenario from agent-based modeling, and then we evaluate with the inventory assessment and impact assessment. We also conducted a case study for this framework. In Belgium, we were observed that people have consumed meat products more than healthy, balanced diet. So in that sense, in the future, if we want to reach the lower carbon scenario in Belgium, we need to consume less meat or use less land use for meat production. And that scenario also tells us if we want to achieve our low carbon scenario, we want to have more bioenergy production. So in this sense, we discovered explore two alternative scenario, having bioenergy crops, miscellaneous for biogas or heat and power electricity production. We assume that they are going to allocate two demonstration farms for the technology in the north or in the south, because we have read the report saying that the main limitation of adopting this technology is because of the lack of knowledge and the lack of incentives. So we first give the demonstration farms located either in north or south, and then we provide, assuming we are going to provide them the incentives. And then from the farmer side, farmers will think about the profits, their farm size, and their familiarity to the crop adoption. From the profits, they will observe their neighboring profit, and they will observe their own current profit for meat production. If the neighboring profit is higher than his own, and he will think about having this new energy crop. And then the farm size is that when you have a bigger size of farm, they will have a higher chance of adopting it because it has less risk aversion rate. And then for the familiarity, we assume that the more close to the neighbor adopters, the more familiar they will be to the new technology. And in the end, after filling into the model, and then each farmer will make decision in every year step, we have a probability to adopt for each farmer. In the end, we have the simulated results. For the environmental impacts, we can see that the environmental impacts are reducing over the time after adopting the energy crop. But it will be different because if the demonstration farms is located in the south or located in the north. Same for the land use function. The production of electricity or energy is increasing, but the meat production is reducing. But same difference between the demonstration farm locations. So this is potentially can be used to support the decision where to allocate the demonstration farm, and also we can support how much incentives needs to be considered to reach the bioenergy target. But this kind of answer needs to be backed up with social science and also local survey data. But so far, what we have done before is based on the open source data and some distribution statistic analysis. It would be nice to have a local survey data to support these kind of decisions. So thank you for this is all. I will stop here.
Thank you. Yes, now, perfect. Thank you, Tianren. Now, let's proceed with our agenda. And let me invite Ryo Koide, researcher at the National Institute for Environmental Studies in Japan, but also a visiting researcher at the Technical University of Delft. Ryu, the floor is yours.
Oh, yes, thanks, Gustavo. I
Ryu?
hope you can see my screen. Yeah.
Can you hear me?
Oh, I'm muted. I hope you can hear me.
Okay,
Yeah,
so
you can hear me, right? And
yes,
the screen is shared, right?
perfect. Now,
Okay,
the
yeah.
floor is yours.
Oh yeah, thanks everyone. So as introduced, my name is Ryu Koide, and today I'm presenting my work on the application of agent-based modeling on circular economy and consumer behaviors. And this is also an effort to couple LCA, MFA in a standardized way and agent-based modeling. And please be reminded that you can ask questions at Mentimeters here. And to begin with, I have to raise two key questions in addressing a transition to circular economy. So one is that, we have growing concern on the rebound effect. So we could answer this question: how can we ensure positive sustainability impact from circular economy strategies? And also, we've been discussing so much about the lack of consumer acceptance, but there have been less studies on the consumer side of circular economy. So the second question is about how can we diffuse circular business models among consumers? And I would argue that to address these questions, we need an agent-based modeling for the early phase assessment of circular economy. So as you know, these mainstream industrial ecology methods being heavily used for circular economy, which is about life cycle assessment. That's quite good for quantifying sustainability impacts, and also material analysis that is quite good for quantifying circularity. However, there are some limitations because these methods are mostly static and also retrospective. And they're talking about mostly aggregated behavior or average behavior, and the model itself doesn't really model the decision making. So if we combine them as agent-based modeling, we have some strengths because these are dynamic modeling, and we can use it in prospective assessment, and we can do exploratory analysis, and we can consider heterogeneity of actors like stakeholders and consumers, and also we can endogenize the decision making of these stakeholders. And the purpose of this study is to develop an agent-based modeling for circular business models, which is covering 7 different circular strategies. For example, repairment, reuse, sharing and leasing and refurbishment of the consumer durables. So it includes B2C and C2C businesses, and incorporating insight from behavior science and life cycle assessment. And the model itself, without empirical data, is published as here in Resources Conservation and Recycling. And here I'm proposing a method to parameterize the model using empirical consumer surveys and also demonstrating scenario and sensitivity analysis. So because of time limitation, I cannot explain all the details, but to provide just an overview, we have households as agent, and then they make a decision on purchasing, maybe repairing or disposing products. And they use product for a certain period probabilistically, and also they're connected through social networks and being influenced by advertisement. And we also have products as more passive entities, and then they become probabilistically broken. And also they are being implemented circular strategies, including repair, reuse, refurbish, or they could be owned by consumers, or they could be leased or rented or shared in case of product service system. And we have more stylized representation of a circular supply chain agent like manufacturer, reuse shop, and a service provider. And then they actually implement circular strategies to products, and they manage product stock. And eventually they will keep inventory every month to calculate the circularity indicators and also environmental impacts like greenhouse gas emissions. And here's the how we model this the products in our model. And we have dynamic and bottom-up circulation of product for every month at the time step. So the product is after being manufactured, it's being purchased by consumers, being used for a certain period of time. It could be broken probabilistically, and then the consumer will have a decision whether to make repair or not. And even if not broken, the consumer may throw it away, and maybe they have hibernate at the product at their home, and they will return it to possibly to manufacturers, or maybe they will throw it away through informal route, or they may resell it to a repair shop, reuse shop, or in case of product service system, it will be returned to a service provider, or maybe handled by the consumer to consumer sharing. And in here, the product could circulate again and again. So we have representation of cascaded use of product, like n times of reuse or being refurbished. And then we have the strengths of ABM, which is modeling the decision making itself. So in circular economy, we have 3 key choices, which is about acquisition, repair, and discharge. So acquisition, the consumer need to choose between buying brand new or buying reused product or maybe renting it. And for repair choice, they may make a decision about whether to repair or not, and then the discharge choice where to let it collect it. And for that, we have we use some theories from marketing sciences and behavior sciences, which is about bounded rationality. So consumer make a decision based on a rational decision at the end, based on price and quality of product services, but they have some screening process because their cognitive resources are limited, and also they are not aware of all different circular business models. So for example, the new sharing service need to be known by the consumer through word of mouth, and then they have social network on the model, or they could be known by advertisement. And then in the end, gradually people will screen out and then make a decision. And also there's social influence. So if the friends in the social network is using, for example, the sharing service, the acceptance to the sharing service may increase. That's the effect counted here. And to make this model, we utilize an empirical way. We have empirically grounded ABM for refrigerator and laptops in the Japanese market. And we do have case study on leasing and refurbishment on these combinations. But the challenge here is that about empirical data, because circular behaviors during use phase are not observable, and generally speaking, public data about the internal decision making is not available. And the circular business models, like sharing service, they're not yet fully implemented in the real world. So it's really difficult to get that real world data for parameterization. And also these empirically grounded circular economy ABM methodology is not yet established. And that's why we went for we went for the implementing our original survey, which is a demographically representative online survey of about 1,000 samples for each product. And we asked a bunch of questions, including the awareness and knowledge of circular business models and their preferences by choice experiment, and also their current and past behaviors, including type of product purchase, whether new or reused or did you rent it, or the duration of the product use and the reason they threw it away, and also where did they discharge the product, and also the social network structures, and also the reception word of mouth and advertisement. And this survey item, we needed to map it to the agent in the simulation. So we had a bunch of data transformation required. I cannot go through all the details, but we learned from Bayesian method and marketing science and some hazardous models and also econometrics models to estimate different parameters. And the challenge is that we wanted to represent the heterogeneity of consumers. For example, some consumer never buy circular models, but some consumers are very prone to circular models. So each agent may have a different parameter, like 80 parameters per each agent. Then if you have 1,000 agents, then we need like more than 80,000 data points. That's a little bit of work estimating from the survey. And here's an example of scenario analysis. So we did comparison of 4 diffusion strategies. Here it means the marketing for P, but one of P is replaced by prolonged strategies, which is about circular economy. So as a wrap up, I'd like to just summarize the contribution of ABM in this field. So we have ABM incorporating LCA and MFA, and then it can implement some circular strategies, simulate circular strategies, and then quantify environmental impact and circularity. And after that, we can have it in the mainstream industrial ecology method, like life cycle assessment or MFA. But incorporating ABM, this means that we can also simulate different diffusion strategies, which is focusing on consumers and behaviors. And also we can incorporate different uncertainty related to behaviors like preferences or other parameters. And then by doing so, we can do the dynamic and prospective assessment or consequential assessment rather than attributional assessment. And also we can do explicit modeling of social side of the system. And when it comes to uncertainty, we can do exploratory modeling, which is not prediction, but to take into account the uncertainty, which strategies will be robust in the end. That type of exploratory modeling analysis we can conduct by ABM. So that's it from my side, and thank you very much for your attention.
Thank you very much, Ryu, for your presentation. And now, if you let me, I'm going to quickly jump to the summary of this session. We have seen 3 very interesting presentations, and in the first part, Jonathan has shown us how spatial explicit features can actually make the decision-making more complex. And it is very important when we're exploring the circularity in the construction sector specifically. Now, in the second presentation, Tianran was also addressing the spatial nature of the importance of spatiality and giving more relevance to consider the territory as a whole when doing an assessment. But at the same time, he incorporated farmers' behavior into the model, which is very important because basically it's showcasing that the supply side by itself, it's far from being just a technical system. It can be a socio-technical system. Finally, from the third presentation, Ryu has showed us that this complexity also appears in the consumption side, especially when we consider consumers' behaviors. This is fundamentally important if we want to understand what is the success or which kind of circularity strategies to implement. So I believe that we have still some minutes to feed some questions. Again, you can ask questions by scanning the QR code or putting this code in at menti.com. Given the time we have, we might be addressing more generic questions, but I invite you to stay after the session is over to ask specific questions. And I've seen some very specific questions and very interesting questions. So I invite people who have made these questions to ask it directly to the presenters after the session is over. We're going to be here. So what time it is? Are we on time? Yes, we're on time. That's super good. So I can actually take a peek on what is some of the questions that have been proposed, and you will have to forgive me, but I've chosen some specific questions that we can address in the minutes we have. More generic questions that we might be addressing in the minutes we have. So this new, where is the limited? Blah, blah, blah. Oh, this is a very, very good one. I think it can even apply for the other presentations. So you have to forgive my improvised dashboard. But the first question that we can address immediately is, have you been publishing your work already? So I invite Ryu, Tianran, and Jonathan to share the links of the presentation of the manuscript if they have papers associated to it in the chat. And I believe that most of this work has been already published, so we can discuss about that later. So let's see the time. Yeah, we're good. I would like to invite Ryu, Jonathan, and Tianran to turn on their microphones so we can start addressing this question. So I've been selecting these 3 questions because I consider that they are very generic, and I think they basically address the main question that we proposed at the beginning. As a reminder, there are also very nice specific questions that are targeted to each one of the presenters, and I invite you to ask them personally at the end of the presentation. So there's the first question that says, you mentioned complex systems. How would you distinguish it from complicated systems? And this question has been made while I was doing this more introduction. So if you let me, guys, I would like to maybe just address it super quick, if that's okay for you. So it's a very important question in when we talk about complex systems, and indeed, complicated systems are different from complex systems. When we talk about a complicated system, we're mainly discussing the difficulty of describing it or deriving properties from it. A clear example could be an LCA model. If you check Equinvent, you have 18,000, depending on the version, of course, you have like around 18,000 processes, and it's a huge network. That's a complicated system. It's more about the difficulty of determining the properties and the flows. It's not a complex system. The difference is that a complex system doesn't have to be particularly difficult, doesn't have to be huge, but it's complex because of the components of the system, meaning that we cannot simply determine the properties of the components without determining the properties of the system. And at the same time, we cannot determine the properties of the system if not determining the properties of the components. So there's an important interaction characteristic here that cannot be easily described with analytic models, the way that we do it in a life cycle assessment or in input-output. I don't know, guys, if you have something to add on top of this.
I can,
Jonathan?
Gustavo, if you want, I can jump in, because I think that in my model, at least how we have started to think about it, it's I don't dare to call it strictly speaking an agent-based model, but it's more a rule-based simulation in that sense at the moment. As soon as you start to add interactions within the environment and interactions within the different agents, that's when the complex behavior or the complex outcomes will arise. And in a way, you are looking at non-linear situations. And I think that in that sense, if you want to, let's say, put in a scale the frameworks of today, mine will be in the lowest end of complexity. I think that the complexity arises with other features of the complication arises with other features of the modeling, such as how to integrate all this data, how computational it is possible to put all these agents in the same place. So I think in terms of complexity, Rio and Tiran are offering more interactions within the agents and their environments.
Thank you, Jonathan. I know, Rio, you would like to add something else, or Tianran? If not, I have a question that it's a general question, and I think those were all of our presenters, and it says, since agents decide, quotation mark, their evolution at every time step, can this pose issues for the reproducibility of the findings? So, I don't know, Tianran, maybe you want to address that first? You can use my microphone. Yeah, just.
Yes, for in our modeling, we calculate for each decision, we run the model multiple times, so that we are sure that the result is in average. But we also have the maximum and minimum value to say that it will be within based on our assumption, the maximum impact will be this, and minimum impacts it will be that. So that will be having some certainty of the reproductivity for the future. But I don't know how others are dealing with this.
Rio, if I'm not mistaken, you were doing sensitivity analysis for that purpose, right?
Yeah, but just to be very quick, I mean, so the ABM is not deterministic model; it's a probabilistic model and stochastic model. So yeah, in terms of reproducibility, if you have the same data and the same random seed and the same coding, it will reproduce. So in that way, we can make sure that it's an experiment. So we can make sure that we can be transparent about that. But at the same time, these are stochastic, so we need to run multiple times of simulation and then consider this uncertainty in the end. And that's also lead to my sensitivity analysis I use in a way to prioritize different parameters, but there could be other way around. I mentioned in deep uncertainty. This is also answering to the complexity. The question about the previous question about complexity, because we have to be in a different mode of research than the traditional industrial ecology. Not to look for the definitive answer or predictive answer, but human decisions and the social interactions is so uncertain. So we have to really consider all the uncertainty parameters and then do the massive parameter sweeping, and then try to find out what would be the ranges, what would be the possible ranges we can reach in some certain policies. And then if you do it in a correct manner, we can evaluate not to really predict the impact of one policy, but instead we say, for example, we take off 3 different policies and simulate, and which policy will be more robust in the sense that that policy can, for example, in my case, policy A can, for example, avoid rebound effect, and then policy B, for example, can achieve the certain amount of greenhouse gas emission reduction, but not like definitive way, but say that, okay, 70% probability or 80% probability. So that kind of uncertain value we have to we have to live with. And then that's biggest difficulty when we explain our result to maybe more traditional industrial ecologists or policymakers. But we have to also show this paradigm, because it's about the future, it's about the behavior and systemic effect.
Thank you very much, Rio, for your answer. I wish that we could jump to more questions. Very interesting, but unfortunately, we have a limited time. So I will invite you to jump to the Mentimeter app to continue with the dynamic part. And if you can go to your phones or your computer, you can see that there's a different question now that says, "What is your field of application?" Guys, can you confirm that? Do you see it? What is your field of application? I can scan the QR code or put the Mentimeter code, and you can start typing your answers. We want to generate a word cloud to see which particular areas are you operating in. So we see agriculture, yes, urban twin transitions, food consumption. So we're going to put a 1 minute to make it super quick. Low carbon industry, sustainable lifestyle, very interesting, related with consumption side. Public waste treatment, circular economy. Yes, we address circular economy a lot today. Food systems. It seems that circular economy and food systems are the fields of application that most of the audience works on. Or energy systems, building use, sharing business. Okay, healthcare. I think I was reading much about healthcare. Very interesting. Healthcare, agriculture. Yes, sustainable aviation. That's interesting. Bioeconomy, consumer products, building use, low carbon industry. But it seems that circular economy, it's the trending topic right now, and it's very reasonable given the context. And time's off. So, okay. Now let's jump to the next question. Yes, and it is, what are the main challenges that we face when we use complexity-oriented approaches? Now, it's not only this question is not only for those that are familiar with ABM, but also for you who doesn't know yet what would be the main challenges. So I can also rephrase it to, what are the main challenges that do you think you will face if you start adopting complexity-oriented approaches? More specifically, agent-based modeling. So you can again now start putting your answers to see what the audience believes is the main challenge when using ABM, for instance, in combination with other industrial ecology tools. I think one of them has already been discussed during this presentation, and is that it's a bit complicated to model the system. Yes, that's precisely what I was believing. Modeling the system, data aspects, uncertainty in consumers' behaviors. That's true. Lack of data, accuracy. Yeah, but that's a very...
Bruce, can you show your screen? I think, or at least I cannot show it. Please.
Terrible mistake of mine. I was not sharing my screen. Okay, now we're talking. I apologize for that. Okay, let's see. Accuracy, behavior data, interpretation, lack of data, data collection, resource time constraints, uncertainty in that's what we mentioned. Cognitive limitations, interesting. Level of abstraction, collaboration, of course, always a problem. Data, software indeed. But here I see that it's more dispersed. Data collection, okay. Data collection, software, data aspect. It seems that in general, if I had to summarize everything, it's more about data. I wonder if it's just a problem of complexity approaches, and if it's not a problem of industrial ecology in general. Data collection, level of abstraction, behavior data. Behavior is always a problem. It's so hard to represent humans in a computational manner. Yes, we don't even understand ourselves sometimes. Okay, time's up. And the next and final question is, what methods and topics would you like to discuss in future events? And as you know, in the initiative, we are planning to organize more seminars, different types of events, but we would like to know, what do you consider is relevant to address? Of course, not only about methodological topics, could be also about more specific issues when using ABM or addressing these complexity-oriented approaches. If I can do this, you can join the Menti using the QR code in case you haven't done it yet. So you can start feeding your answers now. Yeah. Exploratory modeling. Exploratory modeling. Okay. Exploratory definition of complexity. That has to do with theory. Yeah, it's very important. And it's important to mention that it's not only an issue of industrial ecology and ABM. It's like an issue of different scientific fields, how to define what is complex and what is complicated. Handling uncertainty, very important in our field, of course. How ABM really works, that's very interesting. Demystifying ABM. Definition of urban systems, urban energy systems, okay. It's more topic-oriented. Activity-based modeling, aha, I've seen that on mobility. Activity-based modeling, collaborative modeling, rebound effect, very interesting. Externalities, more about ABM, yes. Rebound effect, very important topic in LCA. Model multi-perspectives, statistical analysis. Okay, that's interesting. System dynamics, system dynamics. Maybe we didn't explore much about this particular modeling approach, but it can be coupled as well with ABM. System dynamics. Model multi-perspectives, yes. Certain externalities. Education systems. Okay, that sounds very interesting. More about ABM, statistical analysis. So it seems that it's about ABM, yeah, uncertainty, in-depth methodology related with ABM. It is true. There's a lot still to demystify in this approach because it addresses complexity, but at the same time, it's sometimes very complicated to build this sort of models. So the time is running, and we are reaching the end of this session. And before we finish with this dynamic, this interaction, I would like to invite you to please join the survey that we have at Zoom. Once you leave this session, you will be redirected to a link in which you can give us a little bit of your information if you're willing to contribute to the activities of the initiative, or you have ideas, if you want to also support, you are invited to join the initiative. Now, okay, I have to cut it now. Political ecology, more about ABM for sure. It seems a bit obscure sometimes, and dynamic systems. Okay, thank you very much. So I'm going to finally thank you all for coming to this session in Industrial Ecology Day. I invite you to please visit our website, complexitylca.github.io. There you're going to find more information about what we're doing, some resources and materials. And you can contact us by sending an email to complexity.lca@gmail.com. Thank you very much for your time. This presentation is being recorded, and we are going to send it to you later, and also to the organizers of the Industrial Ecology Day. Thank you to the presenters. Thank you to you all for joining, and until the next opportunity.
And we'll be here for a while, right? So if you have
before I forget,
because in an online event we can have coffee together. So yeah, if you have any specific questions or chatting with us, you can just be here and for a while. Yeah.
Yes. Sorry, I missed that. Indeed, I'm gonna just stop sharing this and